We're now going to look at the geometric series proof. So remember, this proof is examinable as well, so it is compulsory for you to know it off by heart. Step 1 is to add all the terms from the first term to the last term. So from T1 to Tn. Remember that the first term is represented by A, second term is AR, third term is AR squared, and it continues like that up until the last term, which is AR to the power n minus 1. Step 2 is to multiply throughout by R. Multiplying the left-hand side by R, we end up with R Sn. We are then going to multiply each term with R. If we multiply the first term A with R, we have AR. If we multiply the second term, AR times R is going to give us AR squared. So we know that according to laws of exponents, when we multiply the bases that are the same, we add the exponents. So AR squared times R would give us AR cubed. And continuing in this manner, AR to the power n minus 3 times R is going to be AR to the power n minus 2. AR to the power n minus 2 times R is going to be AR to the power n minus 1, and the last term times by R is going to be AR to the power n. So in step 2, we've multiplied throughout by R. The next step depends on which formula you're trying to prove. So remember, for a geometric series, there are two sum formulas. The first one we're going to get is by taking our second equation and subtracting our first equation from it. So we'll have RSN minus SN, that's on the left. Then what we notice is that in our second equation we have AR, and that also exists in the first equation. So when we minus the second equation from the first equation, there are some terms that are going to cancel out. AR squared minus AR squared. AR cubed, remember the next term here is AR cubed, so it will cancel out. All of the terms in between will cancel out as well. The same thing with AR to the power n minus 3. It exists in here. AR to the power n minus 2 cancels out. AR to the power n minus 1. So the only terms that we are left with is AR to the power n from the second equation and A from the first equation. But remember that it is the second equation minus the first equation, so we have AR to the power n minus A. Step 4 would be to factorize both sides. On the left-hand side, we have Sn that is common in both terms, so we're going to pull that out as a common factor, and what we're left with in the bracket is R minus 1. On the right-hand side, A is common in both terms. So we pull out A as a common factor, and we're left with R to the power n minus 1. Step 5 is to make Sn the subject. Now to do that, Sn had this bracket next to it of R minus 1. We're going to divide both sides by that bracket. So on the left-hand side, we're left with Sn, and R minus 1 ends up in the denominator. Now you are familiar with this formula, and you know this is the one that you use when R is greater than 1. But what if the question wanted you to prove the formula where R is less than 1? How would we change the proof so that we can end up with that formula instead? This is what we do. In step 3, we would use equation 1 minus equation 2. So if we go back up to step 3, instead of having equation 2 minus equation 1, we would swap it around. We would have equation 1 minus equation 2. And we would then follow through with the same steps, step 4 and step 5, and this is the equation that we would end up at.